Hello everyone, my name is Adam Malsam. I'm currently a first-year graduate student here at Colorado School of Mines in Geological Engineering, and I'd like to thank you all for attending my virtual presentation here today. My presentation is titled An Analysis of Seasonal Rockfall Trends at Floyd Hill, and without any further ado, we'll get going with this. So the goal of my study, as the title suggests, is to analyze seasonal rockfall trends at Floyd Hill. What I mean by that is that I'm looking to see if there are periods of time within our study period where rockfall activity is increased. Now this might mean higher numbers of rockfall events are occurring, or it might mean larger volumetric rockfall is occurring within certain periods of time. Past studies have shown that rockfall events can kind of parallel triggering mechanisms, such as rainfall or snowmelt. These triggering mechanisms can follow seasonal trends, and thus rockfall can also follow seasonal trends. If I'm able to identify periods of time when rockfall is more common or more frequent at Floyd Hill, then these periods of time would be able to be further analyzed in my research to try and either correlate specific weather events to specific rockfall events, or to see if I can hypothesize a recurrence interval from one large rockfall event to the next rockfall event based on typical rockfall activity at Floyd Hill. Floyd Hill itself is a biotite quartz gneiss rock slope located about just east of Idaho Springs along the westbound lanes of I-70. It's 350 meters wide by 45 meters tall, and it's an area where lots of rockfall activities occurred in the past, including certain large-scale events that have ended up partially closing I-70 in the area. For this reason, CDOT has recommended that Floyd Hill be studied, and that's where I come in. Methods of data collection included using the Faro 3D X330 LiDAR scanner shown in this image here to capture LiDAR scans on average about once every 2.77 weeks. 51 total scans for a total of 50 scanning intervals were collected within this study period, which took place between June 7, 2018 and January 31, 2021. 4 scanning positions were used at Floyd Hill to minimize occlusion and high incidence angles. The idea of occlusion is shown in this image here below the scanner, where the blue scanner and the red scanner overlap in terms of the areas of the slope that they're able to see, but there are also areas that those scanners cannot see that are within their range. So this is represented by the red area on the black slope, which the blue scanner cannot see because of the geometry of the slope, and the blue area on the black slope that the red scanner cannot see because the geometry of the slope blocks the laser beams from the LiDAR from intersecting those portions of the slope. This is why using multiple scanners is important, because it ensures that we get a full picture of the slope that's free of holes or blank areas that might affect our results. A semi-automated workflow is applied in this study. It's important that we used a semi-automated workflow because since we were collecting scans every 2.77 weeks, it requires a lot of processing time to convert those scans from raw point clouds to a complete rockfall database. The first step in the semi-automated workflow is alignment, whereby we have our 4 individual scans taken from our 4 individual scanning positions, and each one of these scans is aligned to the gray base file shown at the base of the image here. Once all of these scans are individually aligned to the base file, they are merged together to form one single merged aligned scan. After we have this merged aligned scan, we classify the rock slope using a mask method. The mask is able to differentiate which areas of the rock slope are bedrock and which areas of the rock slope are not bedrock. By doing this, we're able to separate these two areas, so by the time we finish the classification process, all that is left is predominantly bedrock on the rock slope. After this point, we run change detection. Change detection is the process by which 2 scans, one from one scan date and one from a later scan date, are overlaid on top of each other, and areas where the 2 scans differ, change is calculated. So a change map looks something like this, where we have areas of blue, which represent negative change, and areas of red, which represent positive change. Negative change is typically what we see when we see rockfall, because we have the earlier scan, which is in front of the old scan in that case, and when the rockfall occurs, the front face of the rockfall is suddenly gone, but the back face of the rockfall is still there, represented on the newer scan. So this is why we have negative change in areas where there's rockfall. Clustering, the next step in the workflow, is the process by which areas of measured change are separated out from the rest of the point cloud and clustered together to form their own individual point clouds, which look like this for this rock slope. Now, not all of these clusters are going to be representative of rockfall. Some of them might be vegetation that the classification process wasn't able to identify. Some of them might be the results of complex slope geometry. Either way, we want to remove clusters that are not representative of rockfall. This is done through the volume filtering phase. A random forest classifier was used to remove every cluster that was not rockfall from the total amount of clusters. The random forest classifier essentially uses a training data set where I tell it what is rockfall and what is not rockfall, and then it uses that information in order to use machine learning to judge what is and is not rockfall on its own. Features that it's looking for include the density of points within a cluster, the number of points within a cluster, and other geometric features of the cluster. After volume filtering, we have the following clusters here. Even at this point, some of these clusters might still not be representative of rockfall. There were false positives that the random forest classifier did spit out, along with the true positives, and because of this, I ended up manually filtering out what the random forest classifier spit out to definitively determine what is rockfall and what is not rockfall. So once we have a rockfall identified, we extract them from the slope, and then we use surface reconstruction methods to mesh these point clouds so that we can calculate the volume of these rockfalls. This process is conducted for every rockfall that we identified in this process. And once we have the volume calculated for all these rockfalls, we can compile our final rockfall database. The final rockfall database for Floyd Hill identified 652 total rockfalls for an average rockfall size of around 0.025 meters cubed. This is around 1 foot cubed. The maximum rockfall size we found was 5.4 cubic meters, and the minimum rockfall size was 0.0001 meters cubed, or about 5 cubic centimeters. The minimum rockfall size is important because it highlights the fine levels of change that we were able to detect on the rock slope in order to discover a rockfall of such small magnitude. These two results here are the number of rockfalls per day versus time, and the volume of rockfall per day versus time. The important thing to note from these two figures is that it is seen that there are certain periods of the year, of the time frame analyzed here, where an increased level of rockfall activity is noted. This is between the spring and summer of 2019, where we can see these large jumps in the 5-point centered moving average lines. Outside of those jumps, we see more or less a flat trend line, even though the rockfall data itself is a little noisy. What this shows is that there is a baseline of rockfall activity within this time period where minor rockfall events are occurring, and that baseline of activity is punctuated by these large rockfall events in the spring and summer 2019. This figure shows similar results. This is the cumulative rockfall volume and number of rockfalls versus time. So the cumulative rockfall volume is the blue line, and the cumulative number of rockfalls is the orange line. This figure also shows that the spring and summer of 2019 had an increased amount of rockfall compared to the rest of the time analyzed. The time outside of the spring and summer of 2019 followed more or less a consistent slope, meaning that the rockfall activity was a small scale, but it was consistent. Now, an important thing to notice in this graph is that the spring and summer 2019 represent periods of highly active rockfall, indicated by the large jumps that the lines take. But the spring and summer 2020 don't have nearly as much rockfall occurring. So the question is then, why would the spring and summer of 2020 not have as much rockfall occurring as the spring and summer of 2019? This could be easily explained by the fact that 2020 didn't have as much precipitation as 2019, but even then, the spring and summer are typically Colorado's most active time period in terms of receiving rainfall. So the question then might be, why aren't the spring and summer of 2020 showing an increased level of rockfall activity compared to the time period around them, such as the fall and winter? Because we simply don't see that in this figure. So the explanation, or the hypothesis rather, that this study concluded on was that there's a base level of rockfall activity represented by these kind of consistent slopes in these curves, that's punctuated by highly active rockfall events caused by large rainfall or snowmelt periods. So it's thought that the consistent level of small rockfall activity is caused by conditioning factors. Conditioning factors are essentially forces that act on a rock slope over long periods of time, so hundreds or thousands of years, that gradually destabilize rocks off the slope. These are things like the cut slope trying to revert back to a natural slope angle, climate conditions and seismic conditions that are within normal expected ranges, diurnal temperature changes, and various things like that that act over long periods of time, causing small levels of rockfall. These conditioning factors are thought to be slowly destabilizing rocks, pushing them closer and closer to the edge of the slope, until finally a large storm can come in and kind of flush out all of these rocks that have been slowly destabilized as fully mobilized rockfall. It then might take time for either another large storm to come about, or, as hypothesized in this study, for conditioning factors to continue destabilizing more rock blocks, pushing them closer and closer to the edge of the slope, so that they can eventually be fully mobilized as rockfall by larger triggering factors. So for future study with this research, things I'm going to look to do are expand my rockfall database. So as it currently stands, we have 2 springs and 2 summers to look at. Now, it's not necessarily the most compelling results if you can say spring of 2019 and more rockfall than spring of 2020, because you only have 2 data points essentially to look at. Thankfully, Floyd Hill has data dating back all the way to 2016 that I'm able to incorporate into my database, and I'll continue to take new LiDAR scans to expand the database into the future. Moving forward, I'll try to evaluate if there's any kind of recurrence interval between large-scale rockfall events, and both what's climate conditions, what triggering factors, so rainfall or snowmelt, might be forcing these large-scale rockfall events, and what conditioning factors might be causing the consistent levels of small-scale rockfall activity that we're seeing in between these large-scale events. Finally, I'm going to try to closely analyze these periods of high seasonal activity shown in the spring and summer 2019 to see if I'm able to correlate a specific climate event, so a specific storm, to any kind of specific rockfall activity. And here's my references. So we're going to conclude the presentation at this point. I don't think we're able to take any questions given the format of grads this year, but if anyone has any questions for me, feel free to email me. My email address is amalsam, so AMALSAM, @mimo.mines.edu, and I'll be happy to take any questions that you might have. Once again, thank you for watching this presentation, and I look forward to hopefully seeing people at grads next year for some in-person presentations. Thank you.